So in this lecture, we are going to discuss about the separating a Gaussian. Mixture of Gaussians are often used to model heterogeneous data coming from multiple sources. For example, suppose we have a recording a height of individuals with age of 20 to 30. In between 20 to 30 age peoples, we are measuring the height in one particular city. We know that on an average, a man tend to taller than woman. So obviously, it is scenario that a man will be taller than woman. But so a natural model could be mixture of the Gaussian mixture model is there. So the model is described as P of x is equal to W1 P1 of x plus W2 P2 of x, where W1 and W2 are the weights and this P1, where this P1 represent is Gaussian density representing the typical height of woman, and P2 is Gaussian density representing the typical height of man. In that this W1 and W2 which we have used is the mixture of weight representing a proportion of woman and the city, woman and man in the city. So this W1 and W2 are the mixture of weight representing the proportion of woman and man in a city. The parameter estimation problem for mixture of model in the problem give the access to simple from overall density P. So this is P is overall density. That means height of people in the city without being told that whether the person height is male or female. So this P is gives you a height of the people in the city. You don't know whether the person is male or female. And reconstruction of this parameter distribution. Good approximation is the mean and the variance of P1 and P2 as well as mixture of weights. That will be gives you a good approximation of this. There are taller women and shorter men. For example, if you compare woman height, then it may happen that there are some women which are taller than men, and there are some men which are shorter than women. So Even if one solve the parameter estimation problem for height perfectly, given data point, that means a height, one could not necessarily tell that which population come from, whether it is a male or it is a female. So if I give you a height of the some people, then from height you cannot say that that person is a male person or it is a female person. So in this lecture that we are look at the problem that in some way it is easier and some way it is harder than this problems of height. So we'll talking about the such situation, that means given an height of the person, can we predict that whether that person is a male or is a woman. And sometimes this problem will become very harder and sometimes it will be very easier problem, and it will be harder in that way will interested in the mixture of two Gaussian in high dimensional data. So it will be harder. This problem is very difficult when you dealing with the mixture of two Gaussian in higher dimension data. But it will be easier in that we assume that mean are quite well separated compared to a variance. So what will assume that mean will be quite separate than the variance. Specifically, our focus will be mixture of two Gaussian or mixture of two spherical unit variance Gaussian whose means are separated by the distance omega d raised to 1 by 4. Anybody know what you mean by this omega? What is this notations represent omega? Anyone? So no one is bothered to see what I already told you that you should go through with that notations. There are four types of notations I have told you to go through it. So anyone from you have come across with this notation? Yes. Then how you should understand this? I said that omega d power 1 by 4. Then what should be the meaning of this?
Sample space.
So what I have not understand what you say.
Sample space.
Some sample space. No. Okay. What is the notation? Big O of f. I have told you too many times this f of x.
Order of function.
Order of function. What does it mean of that? It is, yeah, anyone? I have told you this notation 2-3 times, and it is also used in time complexity. I already told you that also. In the time complexity, this notation is used. That is, a time complexity is big O of this much. So the big O notation is this. Suppose if you want to say that g of x is of big O of f of x, then you have fx is less than or equal to c times g of x for every x and for some c greater than 0, where c is a constant. And what does it mean of this omega notation? Instead of less than, there will be a greater than. So when I say that gx so this is actually have written wrongly. Here you have fx and here you have gx. So here g of x is less than or equal to c times fx, and if you want to say that g of x is equal to big omega of fx, then g of x is greater than or equal to c fx for every x and for some c greater than 0. So this is big omega notation and big O notation. So when I say that, what I said that it is the a distance separated by this much, that means big O of d power 1 by 4. So that means fourth root of d. Mean are separated by this distance. That means if you have a one Gaussian and another Gaussian, that distance between them, it is bigger than d power 1 by 4. This f of x here, it is d power 1 by 4 is given. So that distance of mean is bigger than this d power 1 by 4. When I say something is big O of fx, then it says that that function is smaller than this function. That is why it is g of x is less than or equal to c times f of x. So there is the meaning between big O notation and big omega notation. This you should know. And there are other notation is also there. It says that small O notation, when I can say fx is equivalent to small O of g of x if the limit of fx upon g of x as x tends to infinity is 0. This is small O notation. The another notation is small omega notation. When I say that fx is equal to or equivalent to saying that small omega of g of x, if the limit of n tends to infinity, or sorry, x tends to infinity, fx upon g of x is infinity. So this is a 4 notation you should know. Big O notation, big omega notation, small O notation, and small omega notation. And in time complexity, many a times in standard books they have used this notation. Okay, fine. We will show that the level of separation with the high probability, it is uniquely determined which Gaussian in each data point come from. And the algorithm to do so will actually quite simple. And calculate the distance between all pair of points, and points those apart is a small from the same distance or same Gaussian, whereas a points those distance is larger from the different Gaussian. Later, we'll see that with the more sophisticated algorithm, even the separation is of big O omega of 1 is sufficient. That means more than 1 will be sufficient to separate the two probability or two Gaussian of normal distribution will be there. First, we consider just one spherical unit variance Gaussian center at origin. So what we'll consider is, consider one spherical unit variance Gaussian center at origin. So we'll fix with this. We'll start with this. Then we have already discussed one theorem that is known as Gaussian annulus theorem. What the Gaussian annulus theorem says that it formally says that all the probability is concentrated in the thin annulus of width big O of 1 at radius square root of b. So what is the, as per the Gaussian annulus theorem, we already discussed the Gaussian annulus theorem in my previous one of the video, and there where we have talked about that the most of the probability is lies in between the annulus of two. So by Gaussian annulus theorem, most of its probability mass lies on the annulus. What do you mean by annulus? Of width. Yes, anyone? I will also explain you what is the meaning of annulus. Square root of width. Yes, anyone?
If there is a two circles, and so in between the distance of two circles is called annulus.
Yes, it is the area between two sphere in d-dimensional unit space. So if it is a two-dimensional space, then we can talk about the sphere. Here we are talking in d-dimensional space. So that's why there will be two spheres with the same center. Okay, and whatever the volume in between that two spheres, that is known as annulus. That's in two-dimensional, it's represented in this manner. Also, e power minus mod x square by 2. If I can say, what is x bar? X bar, it is an, let us consider x bar is equal to x1, x2 up to xn. Then what will be the mode of x bar? Will be square root of x1 square plus x2 square up to xd square. This is also d. So this I can write down e power minus, if I have modulus a square, so this square root will goes away. It will be x1 square plus x2 square up to so on xd square by 2. So that I can write down a product of, because we know that e power x plus y is equal to e power x into e power y. So as per this argument, we can write down this is e power minus x1 square by 2 into e power minus x2 square by 2 up to so on. That means this all the functions are in the product x minus x b power square by 2. And also we have learned that this and the most of the mass within the slab, that means we have seen that it is near the equator. All the mass is near the equator. That also we have seen. And most of the mass is within the slab. That means we have talked that it is near the equator. Equator is this we have considered, and that is our x is equal to, or x1 is there. So this line is x is equal to some c, and this line is x1 is equal to c, and this line is x1 is equal to minus c. So every mass is lies in this, also that we have proved in one of the lecture. So that is a slab, that is x bar, where x bar is x1 x2 up to xd, such that the x1 is between minus c and plus c. For c is of order 1, big O of 1. This is big O. So pick a point x bar from this Gaussian. Let us pick one x bar. Pick a point x bar from this Gaussian. After picking x bar, from this Gaussian, rotate the coordinate system. So we'll rotate all the coordinate system to make a first axis align with x bar. So we have to rotate the coordinate system to make the first axis align with x bar. Now, once we have pick up one point and we'll rotate that our entire sphere so that the first axis will be x bar. So that is one vector we have chosen in d-dimensional space, and we have fixed our axis on this vector. So suppose what will happen, this is our origin and this is my vector x bar. This vector I have chosen on the unit sphere. Now original axis is this one. This is our original axis. So we have to rotate entire system. So this will become our axis. This is our axis. So that is easily done in the case of Cartesian coordinates. Okay, and as well as in the polar coordinates also one can do. Now after picking this x bar and rotating axis, we'll pick another point y bar, which is independent from x bar. So independently pick a second point y bar from this Gaussian. So we'll pick up another point y bar from this Gaussian. And the fact that most of the probability mass Gaussian within the slab, where this y bar has to be there. So if I pick one point and we already mentioned that most of the mass lies in this slab. So this y bar has first coordinate will be lies in this, it's satisfying this condition. Okay, so that we can say here. The fact that at most all of the probability mass of the Gaussian is within the slab mode of x bar such that minus c less than or equal to x1 less than or equal to c, where c belongs to big O of 1 at the equator. This implies what will happen to this y bar implies that y bar's component along x direction or x bar's direction is big O of 1 with high probability. So that is the situation we have. If we can have one sphere, this is n-dimensional sphere. Once we have pick up, so we have already noted that all the masses lies with this in between these two strips. We already pick up one point and then we'll rotate our entire axis to that point and then we'll pick up a second point. Then as per the argument, most of the masses lies within this strip in between these two straight line. So obviously the point which we are picking up, that is high probability, is it is lies or it will be stay in this in between this two strip. Thus a y bar is nearly perpendicular to x because we already fix our x bar here, because we have x bar we have fixed with the first axis. This is our x bar. So first we have pick up our x bar and we have rotate our entire system with this x bar. So this x bar is here and the y bar has to be here. So that means the angle between these two, x bar and this is our y bar, will be 90 degree. That means they are approximately orthogonal or perpendicular, I can say. So thus I can say that here y bar is nearly perpendicular to x bar. Since it is a perpendicular to x bar, what will be the mode of x bar minus y bar square? So as per the argument, this is mode of x bar minus y bar dot product with mode of x bar minus y bar. So this will gives me mode of x bar minus mode of x bar dot y bar minus, so I'm just making a dot product, that is x bar dot y bar dot x bar, y bar dot y bar. So y bar dot x bar plus y bar dot y bar. But this will gives me 0 because they are nearly perpendicular. Since it is a perpendicular, the dot product between them it is 0. So this will be gives me mode of x bar square, and this will be 0. This is also 0 plus mode of y bar square. So therefore, mode of x bar minus y bar square will be square root of mode of x bar square plus mode of y bar square. This is the situation. This is exactly not equal, but it is approximately same because it is nearly perpendicular. So I am just saying it is approximately same. So that means this distance between x bar and y bar, that is this distance, will be modulus of this plus, so it is a satisfying the Pythagoras theorem. You can just see that, because if this is mode of x bar, this will be mode of y bar, so that has to be mode of x bar square plus y bar square. So as per the Pythagoras theorem, this is our altitude. So I'm satisfying this. Okay, as per this figure. And more precisely, what will be the coordinate system of this y bar or x bar? First we can see. More precisely, since the coordinate system has been rotated so that x bar is at north pole, that is, we have fixed our x bar as a north pole. The coordinate of x bar will be square root of d plus or minus order 1, and all other will be 0. And the y bar, so the coordinate of this point is, we have fixed with square root of d plus or minus order 1, and all other will be 0. So this distance is square root of d. So this distance is the square root of d also because it is the radius of sphere. So this is also square root of d. So what will be this distance? That is between x bar and y bar. Now that you have to give me answer. Till then I will write down this. Since y bar is at most on the equator, coordinate system, so we need to rotate the coordinate system so that the component of y bar is that is perpendicular to north pole in the second coordinate. and then the y bar you will have it is approximately big O of 1 square root of d plus or minus big O of 1 and rest of them are 0. Yes, so have you calculate what will be this distance? Mode of x bar minus y bar. Yeah, you use the Pythagoras theorem. Why you are use this one? Mode of x bar is this square root of d. Mode of y bar is square root of d. So square root of d square plus square root of d square. So that is 2 square root of d square. So what will be this distance?
Root 2d.
Root 2d. That is the things we got. So here mode of x bar minus y bar square. Since we have x bar is this, y bar is this, it will gives me d plus or minus big O of square root of d plus d plus or minus square root of big O of d. So that will be 2 times 2d plus or minus big O of square root of d. And so that mode of x bar minus y bar is equal to square root of 2d plus or minus big O of 1 with high probability. So that means the distance between x bar and y bar will be high probability that they are having this square root of root 2d. Now this we have talked for one Gaussian. Now ultimate our goal is to discuss with the two Gaussian. So we'll have a two Gaussian here. The first Gaussian and another Gaussian. I will pick this two Gaussian with the center is P bar and the center for this one is a Q bar. And separated by the distance is delta. So this distance I am fixing by delta. Okay, so this distance between this one and this one is a delta. The distance between randomly chosen point x bar from the first Gaussian. So I will choose x bar in this Gaussian. So this and I will rotate as in the previous case we have studied. So this is my x bar. And the random chosen point y bar second close to it is a close to that is a square root of delta square plus 2d. Because this is our y bar. Okay, here is y bar and this distance is square root of d, and we should note that x bar minus p bar minus y bar, this q bar, this is orthogonal, so this is 90°. Q bar minus p bar are mutually perpendicular to each other. Okay, let me write down first what I have said to you, that consider two Gaussian two spherical Gaussian unit variance Gaussian with center P and Q bar, P bar and Q bar, separated by delta. The distance between a random point, random chosen point x bar from first Gaussian that we have choose here x bar, and randomly chosen y bar from second Gaussian So we have choose x bar here, y bar will choose randomly from this. See what we'll choose, what we'll do is we'll choose one random point x bar and then we'll rotate everything to that as a north pole. But here, once you rotate this one, here you cannot rotate that one. So this is our y bar. And meanwhile, this is not in two-dimensional. You just think that it is a d-dimensional data is there. Okay, so please don't confuse with the things which is drawn in two dimension. It is actually this all the things is happening in the d-dimensional space. For our visualization, I'm drawing here. So this is y bar. That is a point. So what will be the distance between this x bar and y bar? That is a square root of delta So if I have, this is our z bar. If I have taken this z bar here, then this distance is how much distance between this x bar and z bar? Because these two are parallel, so this is also delta. Now we need to calculate what will be this distance. What will be the delta distance between x bar and y bar? And that is a distance is square root of delta square plus 2 delta. That will prove. And that is our objective. That is a random chosen y bar from the second Gaussian is close to square root of 2 delta square plus 2d. That is exactly I have written. Now why this is so? Since the x bar minus p bar that we have already talked, x bar minus p bar is this factor which is perpendicular to p bar minus q bar, that is this factor. P bar minus q bar, and q bar minus y bar are mutually or nearly perpendicular. So they are perpendicular to each other. So what we'll do is we pick x bar and rotate the coordinate system. So that x bar is at north pole. So that's I've told you that we pick one point x bar from the first Gaussian and will rotate entire system. So that's why this x bar will be a north pole. And let z bar be the north pole of the ball approximating of the equator perpendicular to approximating for the second Gaussian. Now pick y bar. Most of the mass of the second Gaussian is within, as by the same argument, most of the mass is lies within the strip of big O of 1. The equator is perpendicular to q bar minus z bar. So just see that this q bar minus z bar, the equator, that means this is our equator for the second one. So everything is, so for this will be the equator. So entire things is lies in this. So the y bar is high probability that y bar is coming into there, and that is a perpendicular. So this is exactly the perpendicular distance is there, but it is not showing here because it is a d-dimensional space. In 2 dimensions, it is difficult to visualize. But this z bar minus q bar is perpendicular to that distance also. So that's why what we can say is pick y bar. Most of the mass of the second Gaussian is within big O of 1. So the equator perpendicular to q bar minus z bar, and at most all mass of each Gaussian within the distance of big O respective equator perpendicular to p bar minus q bar. So exactly the same things I have represented here. This is perpendicular, this one is also perpendicular. So thus what we can say is mode of x bar minus y bar square is approximately delta square plus mode of z bar minus q bar square plus mode of q bar minus y bar square. So ultimately our objective is to calculate this distance. This distance. So that is the distance is exactly in this triangle we have to see. This is a triangle. This triangle, which I have drawn with the yellow line. So if I want to calculate, so if I draw that triangle here, this is the situation we have. This is our x bar, this is z bar, and this is y bar. So this distance is delta is there. If I can find out this distance, that is the distance between y bar and z bar, then I can apply the Pythagoras theorem to calculate the distance between y bar and x bar. So this y bar, x bar can be calculated using this blue line, blue triangle, that is this distance. Now this is big O of 1, or I can say square root of b plus or minus big O of 1, that we already discussed. This distance is also square root of b plus or minus big O of 1. So this distance y bar minus z bar is this plus this. That is exactly how I've written here. That is z bar minus q by square. That is z bar minus q bar square plus y bar minus q by square plus delta square. So that is this delta square plus what is this is actually distance between z bar minus y bar. Instead of that, we have written. So if you want to, we can do in 2 steps. That you can do it here. That is this blue triangle, if I can draw here, that is, this is our z bar, this is z bar, this is q bar, and this is y bar. This is square root of d. We already know that we have discussed in the, if the spherical here, if one sphere is there, then the situation will be this. And here we have taken a two sphere, so that's why we have this. So we'll have, this is square root of d, this is square root of d, and so this will be square root of 2d. Okay, so that's why this is approximately delta square plus this one is d plus d, d plus or minus big O of square root of d, and this is also plus d plus or minus big O of square root of d, because it is a square, so that's why square root of d will become d. So that's why this is approximately delta square plus 2d plus big O of square root of d, and that completes the things which we have told you, that a distance, that two Gaussian is separated by this much distance, is to ensure that the distance between 2 points are picked from the Gaussian are closer to each other, and then 2 points picked from the different Gaussians are required that upper limit of that distance, that is this much. This will be the upper limit, and the same Gaussian is most lower limit of the distance between 2 points in a different Gaussian. And so that will gives me, this will hold, that means the delta square. So this is 2 root d plus big O of 1 less than or equal to square root of 2d plus delta square minus big O of 1, that is, or I can say that it is 2d plus big O of square root of d is less than or equal to 2d plus delta square, and which is hold, this will be hold when delta is belongs to small omega d power 1 by 4, and thus the mixture of the Gaussian can be separated in this way, and provided their center are separated by this much distance. And what do you mean by this omega? I have told you, small omega, that is fx upon gx, is goes to infinity as x tends to infinity. If we have n points, so if I pick up n points and want to correctly separate all of them with the high probability, we need our individual high probability statement to hold that the probability is of 1 minus 1 upon polynomial function of n square, polynomial function n, that is, polynomial n is actually means the bound of polynomial in n, which means our big O of 1 comes from the Gaussian annulus theorem. It tells you that it is big O of square root of log n, and so it is needed to include extra this much term in the separation of the distance. So ultimate things we need to see that how much distance will be separate between two Gaussian. If you have given a two Gaussian, as we are talking about that male and female problem, they are Gaussian. If you pick up n point out of that, they are separated with this much extra separation will be there. And there is an algorithm for separation point for two Gaussian. For that, what you have to do is you have to calculate all the pairwise distance between the points. So you have to find out all the pairwise distance between the point, and the cluster all smallest pairwise distance must come from the single Gaussian and remove these points from it, and the remaining points come from the second Gaussian. So in that manner, you can separate out the two Gaussian. That means one which having the height of the male, and other one is giving the height of the female. And when one actually separate the Gaussian where the center is much closer. If the center is closer, then it is very easy to separate the Gaussian. So in the next lecture or next, when we'll doing the singular value decomposition to separate the mixture of two Gaussian when their centers are separated by distance of order 1. Okay, so that will be the next, that is comes to the next task when we are dealing with the singular value decomposition. Okay, that's it for this separation of Gaussian that we have. If you have any doubts, you can ask.